Hello, hello, hello. Welcome to the live stream, everybody. Good morning, good afternoon, good evening from wherever you are. Uh, I'm Ryan Sigler. I'm going to be your host for today's live stream and presentation, and I'm a data scientist here at KX. I'm joined here with Michael Ryaboy, who is a developer advocate here at KX. Michael, if you want to say hello.
Hello, hi guys. Thanks for coming.
Yeah, thanks for joining. And today, Michael's going to be doing a really interesting presentation diving into multi-stage retrieval augmented generation. And he's going to be looking at how you can look at the different steps within a RAG pipeline and optimize these different steps and just to really increase the accuracy of your retrieval and to get better results during generation. So really looking forward to the presentation today. And while people are joining, I'm just going to do a little introduction into KDB.AI and who we are and what KDB.AI is. So KDB.AI, it's a vector database. And what we offer, at least for folks that are getting started, is a really excellent free trial. So we believe it's one of the best free trials out there on the market. And to get started, it's very easy. But we offer a free trial that has lots of storage, lots of memory, and unlimited read and writes. So it's really easy to like test this out and understand how it can work for your use case. And the nice thing is that there's no limit for how long you can use it. As long as you're active with it, you will actually be able to continue to use the free trial. And if you want to get started, all you have to do is to go to kdb.ai, click sign up on the upper right there. And once you do that, you'll be presented with a couple of different options. So you'll be able to either sign up for the KDB AI cloud version, or if you wanted to host it yourself, you can sign up for the KDB AI server version. But to get started, I recommend just trying out the cloud version. It's really easy. All you have to do is click that start for free button, and you'll get this form. Just fill out a couple of entries in this form with some information, and then you'll get an email that'll just verify that email address, and you'll get brought to this link where you'll see some directions on how to actually get started. So once you do that, you'll be brought to our cloud portal, and here you'll be able to access your endpoint for KDB AI for your instance, as well as an API key. And you can use these two things then to access KDB AI in your samples and in your Colab notebooks and your applications. But just make sure that when you get this API key, you go ahead and copy that and save it in a safe space. So that way you can access it later, because once you leave this page, you won't be able to access that specific one, though you can always delete your API key and create a new one. One of the awesome things that is built into this cloud interface is that there are code samples and code snippets available right here. So it's super easy just to get an understanding of how to use this. And then if you head over to kdb.ai and check out our Learning Hub, we have many different examples and samples that dive into all the fun and hot topics of the day, like RAG and pattern matching, doing some time series analysis, and all sorts of different awesome samples out there for you. But you can open these up in GitHub and run them in your own Jupyter environment, or if you wanted to check them out in Colab, we have links directly to all the Colab notebooks, so you can get started in there as well. So looking at KDB AI, sort of a bit of comparison to some of the other vector databases out there, DB Engines has us ranked #1. And we've been around for a little while within the time series technology sector. So we have a really efficient time series database, and it's built on a vectorized language. So we've just added similarity search and vector search and the KDB AI offerings to that. So now you can do these really effective and efficient semantic searches over both structured and unstructured data. So that's just a little bit about sort of where we play and where we compare to some of the other vector databases. And Before we get into the session, this session will be recorded, and it is currently being recorded, so it's being live streamed on YouTube and LinkedIn. And once it's concluded, it will immediately be available out there for you to rewatch. Now, we do have a Slack channel that we really encourage you to join. Michael and myself and Neil as well are all members of that Slack channel, and we're happy to answer any of your questions about KDB AI, vector databases, or just like general Gen AI questions or discussion. We're happy to have that. So definitely feel free to join that and join the discussion. Okay, so with that introduction, we will go ahead and start our session for the day. And I'm going to go ahead and switch the deck over to get started with multistage RAG. And what I like to do here is just do a quick sort of rundown of what a vector database is and how this works within like the retrieval and RAG pipeline. And then I'm going to hand it off to Michael to talk a little bit more about the more technical aspects of these different things that you can add into your RAG pipeline. So Michael, if you want to go to the next slide, we could talk a little bit about the vector database and how it works and what's its really core functionality in terms of just retrieving relevant information, and then how can we plug this into a retrieval augmented generation pipeline. So at its core, KDB AI and really any vector database, it's really good at doing similarity searches or semantic similarity searches. And what that means is that based on a user's question or a user's query, it's going to be able to go out and find the most relevant vector embeddings that are stored within it and return those to the user. So that's great because it can do a couple different things. Number one, you could just return relevant embeddings straight to the user. Or number two, you can take these relevant embeddings, relevant pieces of data, and then return them into an application or into the rest of a RAG pipeline. So for example, we can take our retrieved data and then send that to a large language model, which would then in turn sort of complete the RAG pipeline. But how we would set this up in the first place is that we have source data that we're interested in storing within our vector database. So this could be documents, it could be videos, images, really whatever data that you're interested in. You can take that data, you can run that through an embedding model, and the embedding model will output a vector embedding, which is just a numerical representation of the original data. But it's interesting because that vector embedding, it actually represents the semantic meaning of the original data, not just the keywords in it, but the actual meaning of like what is being said and what is meant within the original data. And then that vector embedding is stored in the vector database. So at this point, we can do that retrieval. User asks a question, retrieve the most relevant data based on semantic meaning, return that to our LLM or return that to our user, depending on our use case. So that's like the core foundation of how a vector database works. And if we go to the next slide, when we're doing that similarity search, there's a few different ways that we can do that within KDB AI. So we have these images here, and you can sort of think about this in a simplistic way in a 2D pane where you have the yellow dots that represent the different vectors or embeddings that are stored in our vector database. And then we have a query, which would be the query vector that the user asks. Now that query vector can be compared to all the other vectors in the vector database using some different similarity search methods. In KDB AI, we offer Euclidean distance, cosine similarity, and dot product. So you have options for what the best way to retrieve relevant information is. That'll go and find the most relevant vectors compared to your query vector, and then it'll return those to the user or to send them off to the large language model, depending if we're doing RAG. So that's sort of how this fits in here, right? You have a vector database that's sort of the engine in your retrieval pipeline. It stores all your data in embedded format. You can do similarity search to retrieve the most relevant data from your vector database, and then take that relevant data and send it off to the large language model. So that sort of is the steps in your RAG pipeline. But as Michael's going to be talking about here just in a moment, within each of these steps, there's certain actions that we can take and certain implementations where we can improve these significantly to get the best possible results from each of these steps. Then, of course, to get the best possible generated response from our large language model. So with that, I think we can go ahead and pass off to Michael. Michael, go ahead, take it away.
Hey guys, yeah, so what I'll be talking about next is this idea that a lot of vector database or vector-based applications, uh, they often don't have very good performance because they treat the query and document exactly the same. So we could imagine a vector database where we have some documents, let's say from our documentation, and we chunk them into snippets, and then we embed them and we store them in our vector database. And at the same time, at query time, we take our query and we use the same embedding model to turn that into a vector, and then we find the closest vector in our database of chunks of, let's say, our documentation. And what we often find is that our results aren't very good. And the reason for that is because the query, which is often a question like, how do I install this library, is very different from the actual document that I have, which describes this library in detail. And it could be different in several ways. It could be different in length. The document chunks can be longer. It could be different in structure. It's not a question, it's an actual document. And there are lots of ways we could work around that so that our accuracy is higher. A common one is, for example, that we can take all our documents and ask an LLM, how do we turn this into a question? What is a question? Someone might ask for this. But there are easier ways we could actually improve our accuracy with very little effort. And here we see in just a regular vector DB search, we just get cosine similarity and we return the score. And often for this score, we get 1,000 results, right? Or we get some results that are relevant to our query. They are relevant because they're similar, but the top few results aren't ordered in a very meaningful way because a vector database often, or the vectors in a biencoder, which is what this means, which is the query and document are treated in the exact same way. It doesn't have enough of an understanding of the relationship between the query and the document to order the top few results meaningfully. And for that, there are a few solutions. And the easiest solution is a cross-encoder. And a cross-encoder, I'm going to call a reranker. And what a reranker is it takes every query and document and processes them together through a transformer. And what this allows you to do is, because it processes the query and document together with a very smart model, it could have a more robust understanding of the relationship between your query and your document. What this means is, even if your query and document are structured in very different ways, a cross-encoder can still figure out which document, what is the relationship between the query and the document, and which document is the most similar to the query. So we could think of a reranker as almost a classifier, which classifies the similarity of the document to the query from 0 to 1, and it outputs a score. Now, the benefit of a reranker is that in almost all cases, it just improves recall and accuracy. So what we can do is we can take our traditional vector database and pull some results, pull some documents, 1,000. And these 1,000 documents will have some metric of similarity to our query. They will be relevant. But then we can take a reranker, and a reranker will re-rank these documents that we have. And now, especially for the first few documents, this ordering will be much more meaningful because it will better represent the relationship between the query and the documents. Now, another advantage of re-rankers is it typically takes just one line of code to implement. There are external APIs that do this as an offering. So what you do is you take your, let's say, 1,000 closest documents, you pass them to a re-ranker, and in 100 milliseconds or in 50 milliseconds, they return a response with a ranked ordering of those documents. And this instantly gives you much better results. So for the vast majority of search applications, a re-ranker is almost a necessity because it's just so easy to improve your accuracy with very little work. There are disadvantages to re-rankers though. One big one is that they're much slower than bioencoders, because what we're doing is we're embedding that query and document together at runtime through a transformer. And these transformer models are much smarter than something like a bioencoder, which is just processing them separately previously and is only embedding the query at runtime, which means that especially for longer documents, let's say your query is very long and your document is very long, it's going to be much slower. So I've had cases where the documents are really long and then it takes me 500 milliseconds or even a second to process. Now, the advantage of this is that, especially for longer documents like this, the results are much, much better than a simple vector search. But this latency limit is a big deal. And there are ways to work around it, but fundamentally, you are embedding the query and document at runtime. And another thing is, in practice, these are large, smart transformer models that are doing the re-ranking. They are cross-encoders, so they're not quite a full large language model, but you could think of them as something in the middle, something between a traditional vector database and an LLM. So they do have latency limits, and usually you're limited to about 1,000 documents if you want to see good performance. And if you have really long documents, I recommend even less, and that you experiment with that. Another disadvantage potentially is that re-rankers and traditional vector search only look at direct similarity between the query and the document. And that means if you have a different criteria in how you want to re-rank, for example, if you want to match people to resumes to job descriptions, a re-ranker is going to have a really good performance compared to vector search, but it's not going to have great performance compared to a human who's reading and comparing them, because you don't have an additional metric of compare this based on this additional metric of is this person a good fit. And there are actually clever ways to go around that, like telling the re-ranker, is this person a good fit? And sometimes that works, but that isn't robust enough to be a general kind of advice you could give. And there are all kinds of re-rank models. For example, the most common one and one of the best right now is Cohere Rerank 3, which recently came out. And I recommend for production, you probably want to use that one. But there are other cross-encoder re-rankers, such as Voyage AI has a re-ranker that is a little smaller but faster. And Gina has one as well. I've noticed that Cohere's is better in production, but I haven't run any metrics. So you might want to experiment with some different re-rankers and see which one finds the perfect balance of latency and performance for you.
All right. Michael, I just wanted to add real quick. Anybody, you are welcome to put your questions and comments in the comments, and we'll try to get to those at the end of the session or after the session in the comments section. So,
yeah, thanks, guys. Love questions. All right. So let's look at another strategy for improving the performance of a retrieval. And a really good one is small to big retrieval. And for small to big retrieval, the basic idea is that we have our queries and query and our documents, and our query is very semantically different from our documents. And sometimes if our documents are really large, they are in a completely different place in multi-dimensional embedding space than our query. So one solution for this is we're going to turn our document into tiny little snippets. And then we're going to compare our query to all of those. So we're not going to miss any of those areas of meaning because we're going to compare it to individual sentences or smaller phrases. And what this allows us to do is we could add the document metadata to our smaller documents like our sentences. And then we take all the documents of the sentence, full windows of the sentences that are relevant to our query. And then we use those in our re-ranking step, or we use that in our large language model. And this has all kinds of improvements because we could think of vector search as a very general search that we just want to get the 1,000 closest documents, right? We don't care about the ordering that much because we're probably going to pass them to a re-ranker anyway. But what we really don't want is we don't want to miss any documents. And for that, it's very effective to use something like sentence window retrieval. And in sentence window retrieval, what we're going to do is we're going to take our document and we're going to split it into individual sentences. And then for each individual sentence, we're going to grab the 3 previous and 3 sentences after that sentence, and we're going to store them as metadata. And then at query time, at inference time, we're going to embed our query. We're going to find the closest sentences to that query. And then for every single sentence, we're going to just take the IDs of their parent documents. We're going to eliminate the duplicate IDs. And then we're going to take the parent documents, and then we could either insert them into our LLM, because again, they're going to have larger context and more semantic meaning, because you don't want to insert individual sentences into a large language model because they are semantically without context. So they're very difficult for LLMs and people to interpret. And then we pass them to a re-ranker and eventually to an LLM, or just to an LLM, depending on your retrieval pipeline. And there's all different kinds of small to big retrieval. You don't have to use sentence window retrieval. You can use child-parent recursive retrieval, which means you just have parent chunks, and then you recursively create child chunks. And these child chunks might be a few sentences instead of a single sentence. And you could experiment with that. But sentence window retrieval is what I'm going to go over here because it's mentally very easy to understand. We have this idea of a document, and we have an idea of a sentence. And a sentence is going to have the document, which is going to includes the 3 sentences before and after it as well as metadata. So, okay, let's imagine that we are implementing sentence window retrieval. Well, what do we need in our schema, in our database schema? Well, we need the text, which is going to be our sentence. We need the embedding vector, which is the vector that represents our sentence. And then we need the greater document ID. And this document ID is the ID of the sentence window. So it includes the sentence itself and, for example, 3 sentences before and after the sentence. And then we'll be able to use those documents ID later in later stages of our pipeline. And this way, it's very easy to eliminate duplicates. So we don't have to store this whole document, because we could store the whole document somewhere else. Or we could potentially store the whole document in our schema as well. But in this case, I chose not to. So another bonus is hybrid search with re-ranking. Now, in most applications, we've talked a little bit about how re-ranking just improves performance off the bat. And another thing that often just improves performance off the bat with very little effort is hybrid search. And with hybrid search, you have a little more effort that you're putting in terms of you have this dense semantic vector, which is your vector representation of your sentence's meaning, and you have this sparse query vector, which is just a keyword-based representation of your inbound query. And what you're doing is when you insert your data into your vector database, you're going to insert a dense vector at the same time, and you're going to insert a sparse vector, which you get with an algorithm like BM25. And sorry, I misspoke. You're going to get your sparse vector, And then at query time, you're going to do a BM25 sparse search, and you're going to do a dense vector search. And then you're going to re-rank based on some alpha parameter that you could adjust, which just tells you how important is sentence similarity and how important is sparse, which is keyword similarity. And then you re-rank based on that. So what you do is that in most queries, keywords matter. And just by adding this, you can fundamentally improve performance, especially in applications where keywords are extremely important. Let's say you have financial applications, medical applications where keywords are very important, or you have words in your data set that are likely not, the LLM is likely not to understand completely. So basically, for a majority of applications, even if you set this alpha parameter to be mostly focused on semantic meaning, just giving some priority to keywords improves performance. But we could use what we learned previously to improve this farther. So we have this hybrid search system, but we could just re-rank on top of it and get even better performance. So what this means is that this system is very unlikely to miss 1,000 of the most relevant documents. And then with a re-ranker, we'll just find the top few that we're going to eventually insert into our large language model, or the ones we're going to display to the user. And we can mix and match these. We could use hybrid search with small to big retrieval and re-rank. And you could experiment with these, but these are like small optimizations that you could easily make if you find that in practice, your retrieval accuracy isn't very high. All right, let's imagine a full multi-stage RAG strategy, okay? Imagine you're running a LLM-based application, all right? You're in this application, you have a vector database, and you're finding that your search isn't very good. And you're scratching your head wondering, okay, my search isn't very good. My users aren't satisfied. My large language model isn't putting out good responses because the accuracy is very low, especially for the top case samples. How do I improve this? And what we do in practice is we start with how we process our data originally. So we can imagine a document store where we have our documents. It could be documentation, it could be anything else. And then we pass it through a llama index sentence window parser. And this llama index sentence window parser is a really nice tool that we could use to get this sentence window and the associated metadata. And what it does is it parses the individual sentences, and it also gives us the previous and post sentences as metadata. So very easily, we have this sentence window. And what we could do is we could then pass all the individual sentences through an embedding model. I like to use the fast embedding library, but it doesn't matter which embedding model you use. And then you input all these individual vectors and the associated sentences into a vector database with the sentence window document IDs as metadata. And then at inference time, we take our query embedding, we perform KNN search, take the top K relevant documents. I recommend around 1,000. And then we extract the relevant sentence windows. And then we re-rank the most relevant sentence windows. So for the sentence windows, because of deduplication, you might have somewhere between 500 and 1,000 sentence windows. And then we re-rank them. And then we have a re-rank sentence window. And then we only use, let's say, 4 or 5 of the closest samples, document windows, to actually generate the response. And this is really advantageous because we're able to pass these wider sentence windows into our re-ranking model. And this re-ranking model is going to very well understand the relationship between these wider sentence windows and our query, better than it would understand something like an individual sentence where it might miss additional context. And same with our large language model. Our large language model is also not going to miss this relationship, and is going to take this additional sentence window metadata and is going to be able to output a better result. So that's the our full multi-stage RAG strategy that we'll be demoing in the Colab notebook in a bit. Now, here are some use cases where you might have bad performance. And for these use cases, I actually highly recommend using hybrid search as well. So, for example, legal document search. Keywords matter. You're sifting through lots of legal phrases or citations, and you're finding you might not get really good performance on this with regular retrieval. Human resources and recruitment. Here, a re-ranker is going to be extremely important, and hybrid search can make sure you're getting all the specific skills that you need. But a re-ranker is actually going to understand that maybe this candidate is a good overall fit and is going to see the stuff in the resume that might indicate that this person is a good fit or not. Content recommendation system. Here, a hybrid search might be necessary, but in general, a re-ranker is going to match these preferences extremely well. Chatbot support automation. So in general, where we want to understand the underlying meaning of a user's message, and in these kinds of systems, you have questions that are probably going to be formatted like a question, and you're going to match them to your documentation. And this documentation is going to be structured in a way that's very different from a question. So in this case, again, just by using a re-ranker, we could get a massive improvement in performance. And I think this applies to most applications, where a re-ranker is just a really easy step that we could add on top. So now I want to show a demo of just a Colab notebook where we're going to actually implement this not complex, but RAG strategy that we talked about earlier. So we're going to use small to big embeddings, small to big retrieval, and we're going to do re-ranking. And I've already installed some libraries, so I'm going to skip this step. And I've also imported KDB AI clients. I've added my environmental variables. And I have a table here. And what I'm going to do is I am just fetching my text embedding model from past embed. I'm initializing my Cohere re-ranking client. And I'm importing some libraries from Llama Index, which are going to allow me to parse this data set into sentence windows and fetch the data. So what I'm doing here is let me just download this data set. And this data set is just a Paul essay data set where we're just downloading some of his essays with the Llama Index CLI. And then let's establish a session. And the session is how we're going to interact with our KDB AI database. So it has our endpoint and it has our API key, which I said earlier. And right now we're just making sure that if the table exists, we're going to drop the table. And this is going to take a little bit. And then we'll be ready to initialize our schema, which is going to be exactly what I showed earlier. It's going to have a document ID. It's going to have some text, and the text is going to be our sentence. And it's going to have a vector index. And our vector index is going to be flat because this is in a very large data set. And it's going to have L2 similarity. Again, in this particular case, similarity, you could experiment with similarities. I just chose this metric. And we're going to have 384 dimensions because that's the number of dimensions outputted by our embedding model. Okay, let's wait for this to finish. So what we're doing here is we're creating a table with the schema. And this is going to take a little bit of time just because we're creating a new table in our cloud instance. And then what we could do is we could initialize a node parser. And we're going to read our data from our data set. And this node parser is set to type window. with window size equals 3. So we're taking the 3 sentences before and after. And then let's actually get our nodes and view our parsed nodes. So if I wanted to view parsed nodes, I can do that as well. So it might take a while. Okay, perfect. Yeah, so I have all this metadata on my nodes from llama index, but I actually don't care about most of them. So I'm going to hide this. And then for every single parsed node, what I'm going to do is I'm going to give the parent ID a random, set the parent ID to a random UUID. I'm going to set the parent text to the full window. And I'm going to set the parent text to the correct data. And I'm going to append that text to our dictionary. So to our list, sorry. And now we have a bunch of nodes that we could use with associated metadata. And we can insert those sentences into KDB.ai. So now this takes a minute, so I'm not going to run it right now, but it's run before. So it should be, no, I have to run it because I reinstantiated my table in my database. So what I'm doing here is I'm importing the embedding library from FastEmbed. I'm instantiating it. And for every sentence in that we have, we're going to append the parent ID so we can save it for later. And we're going to add it to our sentences list. And we're just going to embed every single one of these sentences, which means we're creating a vector that represents it semantically. And then we're just going to insert it. We're going to create a data frame with a document ID, text, and embedding in the same format that we had. And then we're just going to insert it into our table. And that's all we're doing here. And the reason we're doing it this way is that we're going to retrieve it from this table afterwards. And the great thing about a vector database is that it can scale to millions or hundreds of millions of vectors. So this allows us to create a process where we could very quickly take these like hundreds of millions of vectors and get the 1,000 vectors that we would want to re-rank later. Now this is magical. It basically means that we could scale up as much as we need, while a re-ranker is very limited to, let's say, 1,000 documents at a time. Just to make sure that we have it inserted, let's query our table. And here we have vectors, we have our individual sentences, and we have the parent ID. And let's do an initial search. And our initial search is going to return some documents, which is going to have our document IDs. It's going to have some text, and it's going to have some vectors. But this isn't extremely relevant for a few reasons. One is that I have individual sentences, and individual sentences can carry only so much semantic meaning. They're going to be very similar to the query, but they're not going to carry as much semantic meaning as we need. But what we can do is we could re-rank. So let's make sure we have the right width, and we could use a re-ranking model. So let's see the re-rank text results for this query. So the query is, how do you decide what to work on? And what we end up with are these sentence windows chunks that are ready to insert into an LLM. And these are about the right size that we want our LLM to see. And they're going to be extremely relevant to our query. Well, how do I choose what to do? Well, how had I chosen what to work on in the past? I wrote an essay for myself. So this is going to be extremely relevant to our query. So this is just a pipeline that I've seen have really good performance, but there are additional optimizations that we can make. We can add hybrid search on top of it. We can also do something like hide, where we turn our individual sentences or documents into questions. We can experiment. We can sometimes, when we really care about the first few results, for example, even a re-ranker isn't going to perform very well. So we can have a more complex pipeline where we have our initial embedding search, we have our re-ranker, and then we have an additional classifier to see whether it answers some sort of criteria. And then we could rank it on individual criteria with, let's say, a large language model. Or we could pass the first few results to a large language model and say, re-rank this. And with how quick large language models are, that's not going to see very high latency. And one of the fundamental limitations of most search systems is that they're not list aware. And so list awareness is this idea that when we're doing re-ranking with Cohere, we're matching every query and document individually, but we're not looking at the other documents around it that might be similar. So LLMs, if you use them correctly, they are list aware. So we can pass them the top 10 documents and say, re-rank these. What are the most qualified applicants to based on this job description? And even though the Cohere results are going to be extremely relevant, an LLM can go even farther and really return the applicants in a very meaningful order of relevancy. And the great thing is we could just scale the model and use a better model when we need better results, or scale down the model when we need better latency. So yeah, that's the whole presentation.
Awesome. Thank you, Michael. Appreciate the presentation. One question for you, actually. Could you fine tune a re-ranker by chance?
Yes, you can, actually. That's one of the most exciting things about re-rankers. You could fine tune. Cohere has a really great re-ranking API. And what you can do, you can re-rank through their interface. You can re-rank through their API. If it's a public cross-encoder, you could re-rank your own cross-encoder and keep it locally if your company doesn't want to use an external re-ranker. And this improves performance by a massive amount. So if you know beforehand what your data will look like, fine-tuning a cross-encoder is going to be a great idea. If your data is more dynamic, then fine-tuning a cross-encoder makes less sense. You could just generally use a cross-encoder and have better performance. But if your data is never changing, let's say you have documentation changes, but let's say you have like some documentation that you're pretty sure is not going to change that much. And in general, even if your documentation is going to change, that's not going to perform your re-ranker's performance that much. It's not going to affect it. So you could fine tune your re-ranker and get better results off the bat. So that's something I really recommend for a lot of applications.
Awesome. Well, thank you for that. And it doesn't look like we have any other questions, but if you think of a question, go ahead and put it in the comments, and we will respond to you after the session as well. And I just wanted to briefly mention here that if you're interested in trying out some of the samples that we have, if you come to kdb.ai and you go to the Learning Hub right here, scroll down, and we have some intro videos how to get started. But we have a whole section on different articles that dive into many of the different hot topics. And actually, one of them is chunking methods, which I think is a really cool one. We talk a little bit about the small to big chunking in there. But we have a ton of different samples to try out. So whether you're interested in like how can you use Hugging Face, or how can I use Llama Index to build an advanced RAG pipeline, maybe you're interested in trying out multimodal RAG, for example. We have a ton of samples in here. So feel free to check it out and try some of these. You can easily open them up in Colab and get started right away. So, all right. Okay. Well, with that, really appreciate the presentation, Michael, and the code walkthrough. Thank you for that. And thanks everyone for joining. Again, if there's any questions, throw them in the comments and we'll get back to you. And with that, we will see you next time. Have a good day, everyone.
Have a good one, guys.